Assalamualaikum warahmatullahi taala wabarakatuh, and very good day to whom is may concern. So this is the lecture for the subject of MEC451 Thermodynamics for UITM student under the program of EM220 and 221. So this is basically a lecture on chapter 4, the second law of thermodynamics. For this chapter, we will divide it into two parts. The first part is about the concept of the second law of thermodynamics, and the second part is about the actual application of the second law of thermodynamics. Okay, let us discover the first part of this chapter, which is the concept of the second law of thermodynamics. This is the outline of this chapter. It is start with the concept of the thermal energy reservoir. From the concept of the thermal energy reservoir, it can be divided into heat engine and refrigerator and heat pump. We also will discuss about the energy conversion efficiency of the heat engine and the refrigeration and heat pump. Then we will discuss about the reversible and irreversible process, which represented the ideal or theoretical as well as the actual thermodynamic processes respectively. Furthermore, I will introduce to you about the Carnot cycle and its principle, which is the theoretical thermodynamic process. Based on that, I will explain about what we call as the Carnot heat engines and its relationship to the heat engine and the refrigeration and heat pump. Upon understanding the concept of the heat engines, the refrigeration and the heat pump, and the Carnot cycle and its principle, we will apply that knowledge to study the entropy principle as well as the isentropic processes. After that, we will apply the entropy principle and isentropic process to the selected steady flow devices, which are turbine, compressor, pump, and nozzle. Finally, I will introduce to you the concept of the exergy. Basically, in this chapter, we will study about the second law of thermodynamics from the basic principle until its application to the steady flow devices. However, the principle of the second law is connection from the first law, or it have the relationship from the first law. Thus, I do hope that you understand the topic of the first law before you proceed to the topic of the second law. In principle, the first law of thermodynamics provides the basic definition of the internal energy, where it is associated with all the thermodynamic system, and it also states the rule of conversion of energy principle. What is meant here is the energy can be transferred into and out of the system. Alternatively, we can say that the energy can travel from the surrounding into the system, and also it can travel from the system to the surrounding. In a conclusion, the first law only concerned about the energy transferred between the system and surrounding. As for the second law, it is concerned with the direction of the natural processes of the energy transfer between the system and surrounding. The second, sorry, the second law said that a natural process in the thermodynamic system run only in one sense or in one direction, and it is not reversible by itself or by natural process. For example, we know that the heat always flows spontaneously from the hotter body to a colder bodies, and never in the reverse direction unless external work is performed on the system. Also, we already know the new property which belong to the second law, which is the entropy. Mathematically, the entropy is written as del Q. So this is the entropy, del Q over T, which is the equilibrium temperature of the system. As I point out in chapter 1, this is mean that the heat energy could not be used to produce work before the temperature of the system achieve the equilibrium temperature, so that at the beginning of the process, the heat is transferring into the system, but that heat is used to make the system achieve the equilibrium temperature only. Based on that, we can summarize that the second law of thermodynamics as the entropy of an isolated system which is not in the equilibrium will tend to increase over the time, and it will approaching a maximum value at equilibrium condition of the system. The figure on the left-hand side is illustrate for the actual natural processes, which is it will occur only one direction and never in the reverse direction. The figure on the right-hand side is illustrate that in an actual thermodynamic process, a process must satisfy both the first and the second law of thermodynamics in order to proceed or exist in the actual system. In another word, the system must allow to exchange the energy between the system and surrounding, and during exchanging the energy between the system and surrounding, it must follow the natural processes, which is the energy will flow from the high degree of quality to a low degree of quality. Basically, there are three major uses of the second law. The first one is the second law may be used to identify the direction of the thermodynamic process. So this is what we call the first major use of the second law. On the figure label number 1, which is this one, as you can see, it is illustrate that the hot coffee in the cup. Naturally, if we just leave the hot coffee on a room, that coffee eventually will be cooled off by itself. On the other hand, if we leave the cool coffee in the similar room just like that, that coffee will never get hot by itself. Thus, from this observation, we can conclude that in an actual thermodynamic process, the energy always travels naturally from higher degree of the energy to a lower degree of energy, but not in the opposite or reverse direction. Therefore, that's what we call as identify the direction of the energy transfer. Next, the second purpose of the second law is actually to assert that the energy has quality as well as quantity. The first law is only concerned about the quantity of the energy and the transformation of energy from one form to another with no regard to its quality. But for the second law, it is provides the necessary mean to determine the quality as well as the degree of degradation of energy during a thermodynamic process. Okay, if we refer to this figure, basically this is figure number 2 to explain the second purpose of the second law. So we can see various type of combustible material as well as their respected specific energy in the unit of megajoule per kilogram of the respected material. As you can see, the highest energy content with the value, the highest energy content with the value which is more than 80 million megajoule per kilogram is the uranium. That means in 1 kilogram of uranium, we have energy more than 80 million megajoule. Conversely, the energy for the petrol, or named as gasoline, is only about 46 megajoule per kilogram. If you refer to the table closely, the energy content in uranium is far higher than other combustible material. Therefore, we only require a small amount of uranium to make a huge combustible or fire. Nonetheless, the uranium is in the category of nuclear energy and it has side effects of radioactive that harmful to the environment, like what has happened to the Chernobyl nuclear power plant. Thus, we need to compromise between energy and safety factor when we are going to select the material used for our thermodynamic system. Okay, now we proceed with the third major uses of the second law. Okay, this is actually used in determining the theoretical limit for the performance of commonly used engineering system, such as heat engine and refrigerator, as well as predicting the degree of completion of the chemical reaction. For an example, if we have designed an engine, let's say for a car, based on the theory, that engine will produce 200 kilowatt of power, then that is called the theoretical limit of the engine. Obviously, the theoretical value is the highest value of the power output. After that, we build the actual engine. From the actual engine, we test the power output. Then the third purpose of the second law, which is determining the theoretical limit for the performance of the commonly used engineering system, will play its role. The power output from the actual engine will never be the same as the theoretical calculation, and it is impossible for the actual engine will have power more than theoretical value. That means that is the theoretical limit. So these are the usage of the second law, which are identify the direction of the energy, assert that energy has quality and quantity, and finally set up the theoretical limit of the engineering system. In the development of the second law of thermodynamics, it is very convenient to have a hypothetical of thermal energy reservoir or just a reservoir. Thermal energy reservoir is defined technically as any body with a relatively large thermal energy capacity, or the mass times the specific heat of the substance, that can supply or absorb the finite or unlimited amount of heat without undergoing any significant change in the temperature. Okay, let us consider two examples to describe the meaning of the thermal energy reservoir. The first one is, if we pour a hot water into the ocean, the temperature of the seawater will not be increased. The second example is, the temperature of the sun is not reducing, although it is radiate the universe every day. Those two examples is exemplify that a body which is supply or absorb the energy without changing its temperature. Basically, in thermodynamic analysis, we have two types of the thermal energy reservoir. The first one is we call it as the source, and the second one we call it as the sink. The source is actually It is used to supply finite amount of heat without undergoing any change in the temperature, and the example for the source is basically sun, furnace, stove, and other things that produce heat. Okay, the sink is actually used to absorb the finite amount of the heat without undergoing any change in the temperature, such as atmospheric air, ocean, lake, river, or other things that receive the energy. Figure aside is illustrate the model of the thermal energy reservoir. The sun will produce heat, that is the source of the system, and the ocean will receive the heat, then it is become the sink. Actually, the thermodynamic study is follow the natural process of the world. Based on this concept, the thermodynamic study can be divided into two engineering systems, which are the heat engine, and the second one is the refrigerator and heat pump. As for introduction, refrigerator and heat pump is actually one system with different purposes. Based on the concept of the thermal energy reservoir, we now can study the first engineering system, which is the heat engine. As I briefed earlier, the heat engine is modeled based on the concept of the thermal energy reservoir, which consists of the source, output, and sink. In the technical definition of the heat engine, it is given as any engineering system that employ a range of methods to apply the heat and to convert the pressure and volume changes into the mechanical motion. Or in another word, the heat engine is used to convert heat to work. Figure aside demonstrate the model of the heat engine. As you can see on that model, the top cloud is the high temperature source. We have learned that the source is used to supply finite amount of heat. Then the source should have the maximum energy with it. Then the energy is transferring into the engineering system, which is in this case is the heat engine. The heat engine that receives the heat from the source is then converted this heat into the work output. Normally, it is in the form of the rotating shaft. After that, the heat that could not be converted into the useful work output is then rejected into the low temperature sink, drawn as the second cloud. The flow of the energy is in the direction of the high to a low degree of energy as per stated in the second law. Also, this heat engine is converting heat into work. The heat engine is basically the concept of the engineering system. If you consider the actual application that lies under the heat engine, which is the engine of the car, the engine will receive high temperature energy from the combustion process of the burning fuel. Then this high temperature energy is converted into kinetic energy of the rotating shaft that make you drive a car. Finally, you will find that the exhaust pipe is very hot, where it is rejected the heat that could not be converted into useful work into the atmospheric air. That is one of many examples of the actual engineering system that fall under the category of the heat engine. Okay, based on that explanation, we can summarize that the heat engine must involve four main processes to convert heat into work. The first one is they will receive heat from a high temperature source in the form of solar energy, oil furnace, nuclear reactor, etc. The second one is they will convert that energy into the heat. They will convert part of that energy into the useful work, usually in the form of the rotating shaft. The third one is they will reject the remaining waste heat to a low temperature sink or to the atmosphere, river, ocean, etc. And finally, they have to operate it on a cycle. Heat engine and other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing a cycle. This fluid is called the working fluid. In the case of MEC451, we will consider three types of the working fluid, which are water, refrigerant R134A, and ideal gas, as we learned in the second chapter of the properties of the pure substance. So these three material or substance is our working fluid in the thermodynamic system. This is another example of the engineering system that categorized under the heat engine, which is the steam power plant. As you can refer to the schematic diagram given on that diagram, we can see that the energy source of the steam power plant is from the furnace. Then the heat from the furnace is transferred into the steam power plant at the boiler. Thus, the process of heat transfer is occur where it is the heat input from the furnace to the boiler, and it is denoted as Q in. Then the steam power plant converted the heat input into useful work at the turbine and denoted as work output or W out. Finally, the heat that could not be converted into useful work will be rejected at the condenser to the river or ocean or atmospheric air, and it is written as Q out. At the same time, the steam power plant required the working input at the pump to pump the working fluid of the water and is denoted as W in. As written here in the slide, the nomenclature for the steam power plant is, so Q in is the amount of heat supplied to the steam in the boiler from a high temperature source. Q out is actually the amount of heat rejected from the steam in the condenser to a low temperature sink, and work out is actually amount of work delivered by the steam at its expense in the turbine, and work in is actually the amount of work required to compress water to the boiler. Based on that, we can define the work net output as the work output of the system minus the work input to the system, and it is similar to the heat input to the system minus the heat output of the system. So these are the equation of the work net that written. The first one is based on the work, the second one based on the heat. Okay, as you can see on that equation, the sign convention is maintained as we define in chapter 3, where the work output and the heat input is positive while the work input and heat output is negative. Thus, once again, I remind you all that this subject is a continuous subject, so that you need to understand the previous 3 chapters before you may understand this chapter. Based on the cycle of the steam power plant and the third major uses of the second law of thermodynamics, the magnitude of the energy used in order to complete the cycle or the performance of the power plant can be measured. This measurement is called the thermal efficiency, and it uses the Greek symbol of eta to represent the thermal efficiency. The thermal efficiency is defined as the desired output or result over the required input of the system. Mathematically, it is written as thermal efficiency is equal to desired result divided by required input. Knowing that for the heat engine, the desired result is the net work output and the required input is the total heat input. Thus, we can write the thermal efficiency for any heat engine as net work output divided by total heat input. Then the thermal efficiency also can be written as work net out divided by Q in, where the work net out is equal to Q in minus Q out. Therefore, we rearrange this equation. We will get also the thermal efficiency is equal to 1 minus Q out divided by Q in. Okay, now we look at this figure. Okay, so this figure. So basically, this figure is illustrate the concept of the thermal efficiency. As we can see on that diagram, which is on the left-hand side, the source produce the energy of 100 kilojoule and transfer it into the two separate systems. This is system number 1. This is system number 2. Okay. Alright. If the first system produce only 20 kilojoule of the network output and the second system produce 30 kilojoule of network output, then the heat waste rejection must be 80 kilojoule and 70 kilojoule respectively. This calculation must comply the first law of the thermodynamics, which is the energy could not be created nor destroyed. Therefore, the balance of the energy must remain unchanged. Okay, based on that, we can calculate the thermal efficiency constructed on the previous equation, and we should get the thermal efficiency of 20% for the first system and 30% for the second system respectively. So that we can conclude that this concept of the thermal energy reservoir, particularly for the heat engine, will apply the second law in determining the thermal efficiency of the engineering system. It will use all three usages of the second law. The first one is the energy must be transferred from high temperature source to the low temperature sink. The second usage is the type of combustible material used to produce the heat source, as well as the type of absorbed material that can absorb the heat rejected. And finally, the third usage of the second law is the heat source is 100 kilojoule, then the maximum work output from that engineering system is only 100 kilojoule, not more than that. Okay, now we look at this figure. So basically this figure, so this is high temperature reservoir. We write it as TH, and the Q high we flow underneath it into the system, and it will produce the work net output. From that one, the waste heat rejected, okay, which is denoted as QL, will be transferred to the low temperature sink of the reservoir as TL. So now we can define the work net is equal to QH minus QL. So the work net, so we can put here, so we can also get the thermal efficiency is equal to 1 minus QL over QH. So basically this is equal to this equation, where in this case Q out is equal to QH, Q in is equal to QL. Based on the third usage of the second law, the theoretical limit, then the general guideline is said that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. In another word, no heat engine can have a thermal efficiency of 100%. Or, as for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. This guideline is known as the Kelvin-Planck statement. Basically, the impossibility of having 100% efficiency from the heat engine is not due to the friction or other dissipative effect. It is a limitation that apply to both idealized and the actual condition of the heat engine. Thus, generally, all heat engines must operate below than 100% efficiency. This is sample problem 4.1, the first sample problem for this chapter. In this sample problem, I will explain about the concept of the thermal energy reservoir in solving the problem of the heat engine. Okay. Alright, let us read the question. The question said that a steam power plant. Okay, the substance is steam, so we have to get the data or the property from the property table of water. Okay, produce 50 megajoule of the network. So the question given the network of 50 megajoule while burning the fuel to produce 150 megawatt. So basically this is the source. Okay, heat transfer from the source. Okay, heat energy at high temperature. So determine the first one is basically the thermal efficiency of the cycle, and the second one, the heat rejected by the cycle to the surrounding. Okay, based on this question, basically we can draw this what we call schematic diagram of heat engine. So we do have a source, and we do have the system, which is heat engine, and we do have the work net output, we have sink. So now Q dot H is equal to 100 megajoule. 150 megajoule. Work net is 50 megajoule. So we don't know what is the value of Q dot L. So remember, dot just mean rate. So based on our equation, so the first one is the equation of the thermal efficiency. Eta is equal to work net output divided by QH. So based on our equation, alright, work net is equal to 50 megajoule and Q dot H is equal to 150 megajoule. So just simple, 50 megajoule divided by 150 megajoule. So now you can cancel what we call, you can cancel the unit. So you can get 0.33. So normally thermal efficiency we represent in the unit of percentage. So we have multiplied by 100%, we can get it 33.3%. So that is the first answer, which is what we call the thermal efficiency of the system. So the second question asks about the heat rejected by the cycle to the surrounding. So heat rejected by the cycle is basically Q dot L. So also based on the work net, we know that work net is equal to Q dot H minus Q dot L. So we can rearrange this equation. We can get that Q dot L is equal to Q dot H minus W dot work net out. So we can get 150 megawatt minus 50 megawatt. So that means the QL is equal to, Q dot L is equal to 100 megajoule. So the heat that has been sink into the, what we call, the heat that has been transferred into the sink is equal to 100, okay, megawatt. Okay, so this is what we call how we are using what we call the concept of the heat engine in order to solve the problem of the power plant. Okay, so basically this is sample problem 4.2, another example under the heat engine. Okay, the question said heat is transferred to the heat engine from the furnace at the rate of 80 megajoule. So this is must be 80 megajoule. So this is must be from the source. So this is must be Q dot H. So based on our system, we put that Q dot H is equal to 80 megajoule. Okay, next it said that if the rate of the waste heat rejection, this is must be Q dot L. Okay, to the nearby river is 50 megajoule, then determine the net power output and the thermal efficiency of this heat engine. It is simple. First one, we draw our schematic diagram. We do have source, we do have system, we do have work net, we do have sink, and we put what we call the heat transfer from source into the system, the heat transfer from the system to the surrounding. Okay, which is this is 80 megajoule, so this is 50 megajoule. So we know that our work dot net is equal to Q dot H minus Q dot L. So we can calculate directly. We can get it as 30 megawatt. So now the thermal efficiency of the heat engine is simple. Eta is equal to work dot net divided by Q dot H. We can get 37.5%. So basically this is just a simple calculation because of this is the concept of the engineering system. This is sample problem 4.3. So basically this sample problem is another example for the heat engine. Okay, the question said a car engine. Okay, the car engine is using to convert the heat into work. It is fall under the category of the heat engine. With a power output of 65 horsepower. So HP is basically horsepower of the engine. So the work net output is 65 horsepower. Has a thermal efficiency of 24%. So this is the data that we have. So the question asks, determine the fuel consumption rate of this car if the fuel has heating value of 44,000 kilojoule per kilogram. That is 44,000 kilojoule of energy is released for each kilogram of fuel burned. So in general, this is the second usage of the second law. So which is the energy has a quality as its own quantity. So that means in one quantity of the fuel, it have the energy of 44,000 kilogram. Or in other words, the quality of the fuel is 44,000 kilojoule in each kilogram of the fuel. Okay. Alright, so that is what we call the information that we have. So now, based on our schematic diagram, so the source, so we don't know what is the value of Q dot H. What we do know, what we call the value of work net is equal to 65 of power, and we do know the thermal efficiency of the engine is 24%, and we don't know the Q dot L. Okay, let us go one by one. So based on the what we call our work dot net is equal to Q dot H minus QL. So also the efficiency of the system eta is equal to work dot net divided by Q dot H. Okay, so then the heat from the combustion, so we can rearrange from this equation. So Q dot H over there, and we can get Q dot H is equal to work net divided by the thermal efficiency. So work net is actually 65 horsepower. So we have to convert this unit 65 horsepower into kilowatt. It's become 48.471. If you use what we call the calculator, Casio 557 something, there is a unit conversion at the back of the calculator. You can use that one. So now we can get what we call the QH Q dot H is equal to 201.963 kilowatt. So this is the answer for the first one, which is the Q dot H. Then from that one, okay, we know that we have to use the knowledge of the fuel consumption. The knowledge of the fuel consumption is basically from the combustion chamber that we have learned in the combustion chamber. So basically Q dot H is equal to Q dot CC, combustion chamber, is equal to efficiency of the combustion chamber time the mass flow rate of the fuel multiply the calorific value Q dot HV. So basically this is equal to, okay, the heating value. So then we can rearrange this equation. We can get M dot F is equal to what we call Q dot H divided by Q dot H. So we can get this value. So we just multiply kilogram per kilojoule per kilogram. So now we can get what we call this one. M dot F is equal to 4.95 times 10 power of negative 3 kilogram per second. Or this engine will use about 5 gram per second. Okay, so that's what we call, you can you also convert the unit from kilogram to gram, so there is no problem. So another you have to correct here is basically this is not QH dot, this is just QHV. Okay, all right, so this is just Q. Okay, so that is the answer for this question. 4.95 times 10 power of negative 3 kilogram per second. Previously, we have discussed the first engineering system based on the thermal engineering reservoir, which is the heat engine that is used to convert the heat into work. Now, I will explain to you the second engineering system that is under the concept of the thermal energy reservoir, and it is the refrigeration and heat pump. By technical definition, the refrigerator and heat pump is a machine or device that moves heat from a lower temperature source to a high temperature sink using mechanical work. We know that the energy will transfer naturally from higher degree to a lower degree of energy. However, the main purpose of the refrigerator and heat pump is to transfer the energy from low degree to a high degree of energy. In another word, the refrigeration and heat pump is used to oppose the natural transfer of energy. Referring to the definition of the heat engine, which is follow the natural process of the heat transfer, then the heat engine will produce the work output. Since the refrigerator and heat pump is oppose the natural process of the heat transfer, then it require the work input. That's why the refrigerator and heat pump will move the heat from a lower temperature source to a high temperature sink using the mechanical work in the form of work input from the electrical component. The refrigerator and heat pump is actually one unit or one engineering system. However, it will have two separate spaces with different temperature. If you may inspect your refrigerator at your home, you will find that the space inside the refrigerator is very cool, where at that space you may keep your leftover food, vegetable, fruit, and others. However, if you check at the back of your refrigerator, you may find it that spaces is relatively hot. What actually be doing by the refrigerator and heat pump is it will remove the heat at the refrigerated space or the cool space to the atmospheric space so that the space at the refrigerated space is become cool. For an example, if you start your refrigerator, the space inside the refrigerator may be at 35 degrees Celsius. So you want to cool down the refrigerator space to let's say 15 degrees Celsius. Then what refrigerator and heat pump system is doing is it will remove 20 degree of the temperature from the refrigerator space to the atmospheric air. So the atmospheric air behind the refrigerator will increase another 20 degrees Celsius. Please do remember that although we are talking about the second law, but the first law is still applicable. Thus, the concept of energy conservation is still applicable here. Therefore, the refrigerator and heat pump is one system but have two spaces with different temperature. One is the cool one, the other one is the hot one. The selection of the space will define its function, either refrigerator or heat pump. Obviously, the real example of the refrigerator is our refrigerator or ice box, where it is used to maintain the refrigerated space at a low temperature by removing heat from it. And the example of the heat pump is the dryer, where it is used to maintain heated space at high temperature. Figure aside illustrate the schematic diagram of the refrigerator and heat pump. It consists of the compressor that require the work input, the condenser to remove the heat to a hot space or heat pump, the expansion valve to change the pressure drastically as well as reducing the temperature is also drastically, normally below negative degrees Celsius. And finally, we have the evaporator to absorb the excess heat from the cool space. So bear in mind, basically in this topic, we are talking about the concept of refrigerator and heat pump. So however, the detail of the study for the refrigerator and heat pump, you will study at the subject of MEC451 Thermal Engineering. So although this is what we call the subject in the semester 2, and thermal engineering is in the subject of semester 5, you have to remember this knowledge since the lecturer for MEC 551 just will use this knowledge directly. Okay, based on the schematic diagram of the refrigerator and heat pump, we can draw the model of the refrigerator and heat pump as illustrated in the middle of the slide. Okay, alright. If you can see that model, the heat is now transferred from the cool refrigerated space to a warm environment. Okay, the third figure on the right hand side is the model of the heat engine, where the flow of the energy is follow the natural process from the higher degree to a lower degree of energy. Basically, the difference between the heat engine and the refrigerator and heat pump is the way energy is being transferred, as you can compare of those figures. So this is basically the refrigerator and heat pump system, and this is the heat engine. So the most important thing is you have to understand, for the refrigerator and heat pump, the heat energy will flow from cool spaces to a system, and then it will have the output at warm environment. And in order to move the heat from cool to the high environment, you need the work input. Okay, as for what we call heat engine, so the heat flow naturally from high to a low temperature, and it will produce what we call the work net output. In the case of the heat engine, the thermal efficiency is defined as the desired output over the required input. And by the third usage of the second law, which is the limitation of the thermodynamic system, then the value of the thermal efficiency must be lower than 100%. However, the refrigerator and heat pump is working opposite than natural process. Thus, the thermal efficiency of the refrigerator and heat pump is named as coefficient of performance, or abbreviated as COP. So all in capital letter. Because of that, the value of the COP is higher than 100%. Surely, it's working opposite direction of the natural process. Therefore, the COP is always presented in the ratio number only without percentage. The definition of COP is still similar to the thermal efficiency, where it is defined as desired output over the required input. Okay, now let us define one by one for the refrigerator and the heat pump. Okay, the first one we look at the refrigerator. We know that the desired output of the refrigerator is the cool refrigerated space, and definitely we need to run the system by giving the mechanical work input to the system. Thus, the COP of the refrigerator is QL over work net in. Okay, alright, so this is the COP of the refrigerator. We know that the work net is equal to QH minus QL. Then we can substitute the work net in the equation of the COP, and it will become COP for refrigeration is equal to QL divided by QH minus QL. So we can simplify this one. It becomes 1 over QH over QL minus 1. So this is what we call the COP, or the performance coefficient of the performance of the refrigerator. Okay, now let us define the COP for the heat pump. Okay. The purpose of the heat pump is basically to supply the heat into the warmer space, such as what we call the dryer. Then the COP for the heat pump becomes, so the COP of heat pump, so desired output, our desired output is QH, or the hot space, divided by required input, which is the work net in. So we know that required input is equal to QH minus QL. So we rearrange this equation, we can get COP heat pump is equal to 1 over 1 minus QL over QH. So, or in another way, we can say that COP heat pump is equal to COP refrigeration plus 1. So this is always true. Okay, alright. In this slide, we will learn about the Clausius statement. Basically, the Clausius statement is the limitation for the refrigeration and the heat pump system. It is basically similar to the Kelvin-Planck statement for the heat engine system. The Clausius statement says it is impossible to construct a device that operates in a cycle and produce no effect other than the transfer of the heat from a lower temperature body to a higher temperature body. It states that a refrigerator and heat pump system cannot operate unless its compressor is driven by an external power source, such as an electrical motor. This way, the net effect on the surrounding involves the consumption of some energy in the form of work, in addition to the transfer of the heat from a colder body to the warmer one. To date, no experiment has been conducted that contradicts to the second law, and this should be taken as sufficient proof of its validity. As I pointed out previously, both Kelvin-Planck and Clausius statement is the limitation to the heat engine and the refrigerator and the heat pump system respectively. The Kelvin-Planck and the Clausius statements are equivalent in their consequences, and either statement can be used as the expression of the second law of thermodynamics. Any device that violates the Kelvin-Planck statement is also violate the Clausius statement, and vice versa. The heat engine could not convert all heat into work without leaving part of it into the surrounding. Refrigerator and heat pump need external power to move heat from low to a high temperature medium or spaces. This is sample problem 4.4. to discuss specifically for the problem of the refrigerator system. Okay, let us see the question. The question said the food compartment of a refrigerator is maintained at 4 degrees Celsius by removing heat from it at the rate of 300 kilojoule per minute. If the required power input to the refrigerator is 2 kilowatt, determine the coefficient of performance of the refrigerator or COP and the head of rejection to the room that houses the refrigerator. Okay, so basically this is the hotter room. Okay, because the colder room is in the refrigerator and we put refrigerator in our house. Okay, from that one we can draw our cloud of the system. So this is high temperature, okay, sink. So this is low temperature source, 4 degrees Celsius. And then in order to maintain this 4 degrees Celsius, the system must remove 360 kilojoule per minute of heat, okay, by using work input of 2 kilowatt. Okay, so now the COP, we have learned that COP for the refrigerant is equal to Q dot L, because for the refrigerator, we're interested in the colder room. So Q dot L divided by work dot net. So we know that is 360 kilojoule per minute divided by kilowatt. We have to convert the unit. So because kilowatt is basically kilojoule per second, we have to change the unit this one. So now we can get COP is equal to 3. So please do remember that we do not need to convert the ratio value into percentage as we do in the thermal efficiency. Otherwise it becomes 300%. So when you talk to people, you have COP 300%, people will getting weird. So we just said that COP R is equal to 3. Okay, so the next question is what is the rate of the heat rejection or the Q dot H? So we know that Q dot H is equal to Q dot L plus work dot net in. Okay, so we know this one from the equation of work net in. So we can rearrange this equation. So now we can get Q dot H is equal to 480 kilojoule per minute. So this is how we are using what we call the concept of refrigeration in order to solving the refrigerator system. Okay, this is the sample problem 4.5. So in this sample problem, I will explain to you how to solve the problem of the heat pump. Okay, in this question, it said that a heat pump is used to meet the heating requirement of the house and maintain it 20 degrees Celsius. On a day when the outdoor air temperature drops to -2 degrees Celsius, the house is estimated to lose heat at a rate of 80,000 kilojoule per hour. If the heat pump under this condition has a COP of 2.5, determine the power consumed by the heat pump and the rate at which heat is absorbed from the cool outdoor air. Okay, basically in this question it said that we have a room. So this is a room. In this room, we have a temperature about 20 degrees Celsius. So outside of the room, we have -2 degrees Celsius. So now the heat is losing from this room into surrounding at the rate of 80,000 kilojoule per hour. So what we want to do now, we want to use the heat pump to maintain the temperature in this room at 20 degrees Celsius. Therefore, if the room lose the temperature of 80,000 kilojoule per hour, then our heat pump system must pumping the heat at the similar rate, which is 80,000 kilojoule per system. So in order to pump 80,000 kilojoule per hour, so what is the work net input we require? and what is the rate of heat from what we call the colder space that have been converted into what we call our system. Okay, the first one we have to see this one. So this is what we call the power consumed by the heat pump. Okay, so work net, basically work net input. So COP HP is equal to Q dot H divided by work dot net in. So from this one we can rearrange, we can get work net in is equal to Q dot H over COP HP. So 80,000 divided by 2.5, we can get work net in is equal to 32,000 kilojoule per hour. So the second question is about the rate at which heat is absorbed from the colder outdoor air. So we know that from the equation of work net in is equal to Q dot H minus Q dot L. So we know the value of QH, we know the value of work net in. So then we can easily calculate the Q dot L. So the value is actually 48,000 kilojoule per hour. So basically this is what we call the concept of the thermal energy reservoir, which is we have what we call the sink, and we have the source, and we have the system. Okay, so in order to solve the problem of the heat pump. Okay, now we will discuss about next topic, which is about the reversible and irreversible processes. As a general rule, when the system undergoes a change from its initial state to the other state, or we call it the final state, the system is said to have undergone a process. During the thermodynamic process, one or more properties of the system, such as temperature, heat, pressure, volume, enthalpy, or entropy, or etc., changes. Based on that process, the second law of thermodynamics enables us to classify all the processes under two main categories. The first one is the reversible process, or it is known as an ideal processes, and the second one is the irreversible process, or sometimes we call it as natural processes, and it is actually the actual process. So that the reversible process is the theoretical or ideal process, and the irreversible process is the natural or actual process. The reversible process is technically defined as the process in which the system and the surrounding can be restored to the initial state from the final state without producing any changes in the thermodynamic properties of the universe. That means the reversible process can be reversed completely, and there is no trace left to show that the system has undergone thermodynamic change. It seems like when we walk on the sand, it will leave the trace of our shoe. Reversible process means when we walking reversely on the same sand, the trace of our shoes will lost completely, like we rewind the movie. That is the meaning of the reversible process, and the keyword is leaving no trace. Basically, there are two important conditions for the reversible process to occur. The first one is the process should occur in infinitesimally small time, and the second one is all of the initial and the final state of the system should be in equilibrium with each other. As I said earlier, the reversible process is the theoretical or the ideal process where in actual practice the reversible process never occurs. It only the hypothetical process. In the thermodynamic study, we are interested in the reversible process because of two main reasons. The first one is they are very easy to analyze, and the second one is they serve as idealized model or the theoretical limit which actual process can be compared. Therefore, we need the reversible process in our thermodynamic analysis. The irreversible process is also known as actual or natural process because all the processes occurring in nature or in actual system are irreversible processes. The natural process occur due to the finite gradient between the two states of the system. For instance, heat flow between two bodies occur due to the temperature gradient between the two bodies. This is in fact the natural flow of the heat is obey the first usage of the second law. Similarly, water flow from high level to a low level. Current move from high potential to a low potential. All of them occur naturally. In the irreversible process, the initial state of the system and surrounding cannot be restored from the final state. If you mix hot water, sugar, and coffee, then you cannot undo the mixing process and separate back the hot water, sugar, and coffee respectively as before you make it. During the irreversible process, various states in the system on the path is changing from initial state to the final state are not in equilibrium condition with each other. Also, during the irreversible process, the entropy of the system increases decisively and it cannot be reduced back to its initial or original value. The phenomenon of a system undergoing irreversible process is called as irreversibility, and it is defined as the factor that causes a process to be irreversible. In general, the irreversibility is due to two main factors, which are number one is the non-equilibrium condition of the actual process, and number two is the increase of entropy whenever the process occurs. Therefore, the component of the irreversibility include the friction, unrestrained expansion, mixing of two or more fluids, heat transfer across a finite temperature difference, electric resistance, inelastic deformation of solid, and chemical reaction. If we're referring back to the reversible process, basically, the reversible process can be divided into three areas. The first one is the internally reversible process, where if no irreversibility occur within the boundaries of the system during the process. The second one is the externally reversible process, where it is mean if no irreversibility occur outside the system boundaries. And the third area is totally reversible process, which is it is involve no irreversibility within the system and its surrounding. A totally reversible process involves no heat transfer through a finite temperature difference, no non-quasi-equilibrium changes, and no friction or other dissipative effect. The illustration of the reversible process, totally and internally reversible heat transfer processes is given on this slide from the left to the right figures. Okay, now we will discover about the Carnot cycle. The Carnot cycle is actually a theoretical ideal thermodynamic cycle that have been proposed by a French physicist named Sadi Carnot in 1824, and this cycle has been expanded upon by others in the 1830s and 1840s. The Carnot cycle provides the upper or the maximum limit on the efficiency that any classical thermodynamic engine can achieve during the conversion of the heat into the work, or conversely, the efficiency of a refrigeration system in creating a temperature difference by the application of work to the system. It is not an actual thermodynamic cycle, but it is just a theoretical construct. Therefore, please note that the Carnot cycle does not exist in the actual condition. The Carnot cycle, which is an ideal reversible closed thermodynamic cycle that can be modeled as a frictionless piston cylinder device as shown in the diagram given in this slide, in which the working substance goes through the four successive operations. The first one is the isothermal expansion to a desired point that is labeled as number 1 on the slide. For this purpose, the substance receives heat from the high energy source such as furnace, combustion process, or etc. Then the temperature of the substance will be increased as well. Since the temperature is directly proportional to the pressure, thus the pressure of the substance is also increased. Due to the condition of the piston cylinder device is frictionless, then any increase of the pressure will push the piston outward and produce the work output. The second process that has been labeled as number 2 is the adiabatic expansion to a desired point. For this process, the substance is hot since it received the high energy from the source from the first process. Now, the piston cylinder device is insulated so that no heat transfer can cross its boundary. In order to return the temperature of the substance to its original or initial temperature, then the pressure developed due to the temperature difference between the initial temperature will push the piston upward and also will produce the work output. The figure labeled number 3 is illustrate the third Carnot cycle process, which is the isothermal compression. This is done by imposing the low energy sink to a piston cylinder device. When this process occurs, the energy from the substance will naturally transfer to a low temperature sink and leave the low temperature substance in the piston cylinder device. Since the substance is losing its energy, then it will suck the piston to reduce its volume and compensate to its temperature. Thus, we got work input for this process. The fourth process is the adiabatic compression back to its initial state, and it is labeled as number 4 on this slide. Now, the temperature of the substance is lower than the initial temperature. Also, the piston cylinder device is insulated so that no heat energy can be transferred to the surrounding. Therefore, in order to rise the temperature of the substance back to the initial temperature, then the substance will suck the piston again to reduce the volume so that it can compensate with the initial temperature. Therefore, again, we will have the work input to the system. Those are the 4 processes of the Carnot cycle. Please keep in mind that they are actually the ideal reversible process and is only exists in the theoretical condition. not in the actual condition. That's why they are called as reversible isothermal expansion, reversible adiabatic expansion, reversible isothermal compression, reversible adiabatic compression, respectively. As we know that the Carnot heat engine cycle is a totally reversible cycle. Therefore, all the processes that comprise it can be reversed, in which case it becomes the Carnot refrigeration cycle. The PV diagram on the left-hand side illustrates the PV diagram for the heat engine, and the PV diagram on the right-hand side is illustrate the PV diagram for the refrigeration and heat engine. For the Carnot system, please do remember that they can be reversed. Since the Carnot heat engine cycle is a totally reversible cycle, then the efficiency of an irreversible heat engine is always less than the efficiency of the reversible one operating between the same two reservoirs. That means the efficiency of the actual heat engine must be less than the ideal one. It also means the efficiency of all reversible heat engines operating between the same two reservoirs are the same. Those figures on this slide illustrate those conditions. Based on the condition of the Carnot heat engine cycle, we are now can define the thermodynamic temperature scale. The thermodynamic temperature scale is defined as a temperature scale that is independent of the properties of the substance that are used to measure the temperature. It said that the ratio between the heat is equivalent to the ratio between the temperature, so that QH over QL in the reversible condition is equal to the TH over TL as written in this equation. But the value of QH is not equal to the value of the TH. Similarly, the value of QL is not equal to the value of TL. This temperature scale is also called the Kelvin scale, and the temperature on this scale are called absolute temperature, which is calculated in the unit of Kelvin. This temperature scale offers a great conveniences in the thermodynamic calculation. Please note that the actual conversion between the degree Celsius and the Kelvin is 273.15. However, for simplification purposes, our subject MEC451 will use only the value of 273. Based on the thermodynamic temperature scale, we can make the relationship between the heat engine and the Carnot heat engine. We have derived the thermal efficiency of any heat engine in the slide number 8 as 1 minus QL over QH. Therefore, since the relationship of the thermodynamic temperature scale is equal to QH over QL in the reversible condition is equal to the TH over TL, thus the thermal efficiency of the Carnot heat engine can be written as 1 minus TL over TH. Okay? The thermal efficiency of the actual and reversible heat engine operate between the same temperature limit is compressed as follows. Number 1. If the thermal efficiency of a system is less than the thermal efficiency of the reversible or ideal or theoretical or Carnot system, then the system is an actual or irreversible process. Okay, number 2. If the thermal efficiency of a system is equal to the thermal efficiency of the reversible or the ideal or theoretical or the Carnot system, then that system is the reversible or ideal or theoretical or Carnot system. Number 3. If the thermal efficiency of the system is higher than the thermal efficiency of the reversible or ideal or theoretical or Carnot system, then that system is impossible heat engine system. This is actually the importance of having the efficiency of the Carnot heat engine, where we can identify the system, either it is actual, reversible, or impossible system. Okay, this is sample problem 4.6. In this sample problem, I will demonstrate to you how to solve a problem regarding to the Carnot heat engine. Okay, the question said a Carnot heat engine receive 500 kilojoule of heat per cycle from a high temperature heat reservoir at 652 degrees Celsius and reject heat to a low temperature heat reservoir at 30 degrees Celsius. Okay, from this statement, basically we can draw our model of the heat engine. So at the high temperature reservoir, we have 625 degrees Celsius and it is transfer the heat at the value of 500 kilojoule to the system of Carnot heat engine, and that Carnot heat engine will produce the work net, and it also will transfer the unuseful heat into the low temperature sink, and low temperature reservoir, the temperature is 30 degrees Celsius. So now the question asks us to determine what is the thermal efficiency of this Carnot heat engine and also the amount of heat rejected to a low temperature reservoir. So efficiency and basically QL. Okay, so the thermal efficiency, as we derived before, the thermal efficiency in the Carnot heat engine or in the reversible condition is equal to 1 minus TL over TH. Please do remember that original equation for the heat engine is 1 minus QL over QH. However, the ratio of the temperature scale is QL over QH is equal to TL over TH. Then we can substitute that TL over TH in our equation. So we do have the low temperature as 30 degrees Celsius and we do have the high temperature as the 652 degrees Celsius. Now the unit is in degrees Celsius. As I mentioned earlier, we have to convert the unit from degrees Celsius into the Kelvin. So we use 273. Okay, if you see mathematically, you cannot cancel out this 273 because of the plus sign here. It's not multiplication. It's multiplication. Yes, mathematically we can cancel out. So now the value is basically 0.672, which is we can convert it into the what we call percentage as a 67.2%. Okay, so B. So B, the question asks us what is the amount of the heat rejected to the low temperature. Okay, so this is basically we use what we call the temperature scale, which is QL over QH is equal to TL over TH. So from this one, we can arrange the equation as QL is equal to TL over TH multiplied by QH. So we put all the value, we should get the value of Q low is equal to 164 kilojoule. So that means the energy that cannot be transferred into useful work is equal to 164 kilojoule. So this is how we are going to use what we call the Carnot heat engine and the what we call the most important thing, the temperature scale here. Okay. Recall that the second usage of the second law is assert that the energy has its quality as well as quantity. Basically, the relationship between the quality and energy is directly proportional, where the higher the temperature of the source, the higher its quality. Therefore, in order to increase the thermal efficiency of the Carnot heat engine, we need to increase the temperature of the source. As you can see here from this diagram, at 925 Kelvin, the thermal efficiency is approximately 67%. As the temperature of the source is keep reducing, as you can see here, from 925 to 350, the thermal efficiency also reduced to 13.4%. Since the calculation of the thermal efficiency of the Carnot heat engine involve the ratio and the conversion unit between Kelvin and Celsius is additional, then we could not use the unit of degree Celsius in the calculation of thermal efficiency of the Carnot heat engine. As you can see here, this is the basic equation for the thermal efficiency for the reversible cycle or the Carnot cycle, which is it use the ratio between the lower temperature and the high temperature. So this diagram basically showing us what we call how we are going to increase the thermal efficiency of the Carnot heat engine, whereas by increase its temperature. The COP of a reversible refrigerator or heat pump is the maximum theoretical value for the specified temperature limit. Actual refrigerators or heat pumps may approach this value as their design are improved, but they never can reach the ideal value. As usual, actual value could not match the theoretical value. The COPs of both the refrigerator and the heat pump will decrease as the lower temperature or TL is decreases. That is, it requires more work to absorb heat from a lower temperature media. The COP for any refrigerator is basically 1 over QH divided by QL minus 1, as you can see on this slide. And the COP for refrigerator in the ideal system can be written as 1 over TH over TL minus 1. So in this case, we can convert the value of QH over QL from the actual refrigerator to the TH over TL for the reversible refrigerator. Similarly, the COP for the heat pump is actually 1 divided by 1 minus QL over QH. And for the reversible cycle, we can change this value, which is QL over QH, to the what we call TL over TH as written on this slide. So in general, the coefficient of the performance of the actual and reversible refrigerator operating between the same temperature limit is compared as follows. So this is basically to show you how we compare the actual COP with the reversible one. Okay, number one. Okay, if the COP of a refrigerator is less than the COP of the reversible one, then the system is irreversible refrigerator, or this is what we call the ideal cycle. So number two, if the COP of the refrigerator that we calculated is equal to the COP of the reversible one, then that system is actually the reversible refrigerator, or that's one is the ideal refrigerator. So finally, if the COP of our refrigerator that we have been calculated is higher than we get from what we calculated, based on the ideal one, then that system basically is the impossible system, or we call it impossible refrigerator. This is a sample problem 4.7. Basically, this is sample problem to exemplify the usage of the principle of the Carnot refrigerator in solving the typical thermodynamic problem of the refrigerator system. Okay, in this sample problem, it said that an inventor claimed to have developed a refrigerator that maintained the refrigerated space at 2 degrees Celsius while operating in a room where the temperature is 25 degrees Celsius and the system has a COP of 13.5. So the question asks us, is there any truth in this claim? Okay, so that the system has COP of 13.5 and the cooler temperature is 2 degrees Celsius and the surrounding is basically 25 degrees Celsius. Please do not confuse with this sentence where is a room where the temperature is 25 degrees Celsius. Basically, for a refrigerator, we put it inside our house so that the surrounding of the refrigerator is called what we call room temperature. Okay, so based on this one, we can using what we call the equation of COP refrigeration. Okay, where ideally, the actual one is QL divided by QH minus QL. So we can change this ratio into the temperature because this is the ratio. So we can change it into low temperature divided by high temperature minus lower temperature. So basically this is all the ratio. From this one, as I said earlier, we have to use the unit of Kelvin. So 2 degrees Celsius plus 273 divided by 25 minus 2. If you can see here, so at the denominator, for TH and TL, I'm using 25 degrees Celsius and 2 degrees Celsius. This is because if you add up 25 with 273 minus 2 plus 273, then basically 273 that you add up at the 25 degrees Celsius will be cancelled out with 273 that you add up with the 2 degrees Celsius. Basically, the magnitude is the same because the function here is basically the minus function. It's not multiply. If you multiply, then you have to use what we call the full number. Then the answer you get, the COP for this refrigeration is basically 11.96. So why we are using the TH over TL? Because at earlier stage, we have studied that this is what we call the COP for the ideal process. So that means the ideal is the maximum COP that you can get. So that from this one, the maximum COP you can get is 11.6, but the inventor claim to have 13.5, then this claim is basically false. So this is how you relate what we call the actual COP with the ideal COP. Okay, so this is another sample. So this is sample 4.8 that is exemplify the usage of the principle of the Carnot heat pump in solving the typical thermodynamic problem of the heat pump. Okay, so this question said that a heat pump is used to be to heat a house during a winter. Yes, so for the heat pump we want what we call the high temperature space. The house is to be maintained at 21 degrees Celsius all the time. So the house is estimated to be losing heat at the rate of 135 kilojoule per hour when the outside temperature drop to -5 degrees Celsius. So we are asking to determine the minimum power required to drive this heat pump. So what we have here is basically, so this is our space. We want to keep it 21 degrees Celsius, but during the winter we know that the surrounding is -5 degrees Celsius. Since the system is connected to the surrounding, so at any time it will lose the heat. About 135,000 kilowatt of kilowatt of heat has been rejected from the house, been losing from the house. So in order to maintain it at 21 degrees Celsius, the heat pump must pumping the heat at the rate of 135,000 kilojoule per hour, similar to the heat that we are lost. So from this one, the question asks us to determine what is the minimum power required. Okay, so we know that the rate of work, the power input is equal to the rate of heat that we pump into our system minus the Q dot L. So from Carnot principle, QH over QL in the ideal system or in the reversible system is equal to TH over TL. Okay, over TH over TL. Then we can rearrange to this equation to determine the Q dot L. So from this one we can get TL over TH. It's okay. So don't be confused. This is, you see, Q dot L, but this equation only QH, Q without dot. So basically the dot, if you dot here, so the denominator also you need to be dot. Okay, so that one they will cancel out what we call the unit. So then is equal to TH over TL multiplied by Q dot H over Q dot H. You can get the value of 268 divided by 294 multiplied by 135,000. So we can get what we call our heat that have been rejected is 123061 kilojoule per hour. So from this one we can rearrange, so we can put what we call our value of Q dot L here into this equation. So Q dot H is equal to 135000 minus 123061. So you will get it 11938 kilojoule per hour, or we can convert it into kilowatt. So by divide, 1 hour is equal to 60 seconds. So that means you can get it 3.32 kilowatt. Okay, so this is how you are going what we call to use the heat pump system based on the Carnot heat engine. Okay, so now we have finished the first part of chapter 4, which is the second law of thermodynamics. As a summary, the first part is exploring the concept of the second law that have been modeled based on the thermal energy reservoir. From that model, we can define the heat engine and the refrigerator and heat pump. The heat engine and the refrigerator and heat pump is then compared to the ideal system, which is known as the Carnot cycle. None of the heat engine and the refrigerator and heat pump systems can have higher thermal efficiency or COP that higher than Carnot cycle. And the actual system must have lower thermal efficiency or COP than the Carnot system respectively. Based on that, we can define the thermodynamic temperature scale to compare between actual and theoretical system. Therefore, that's all for the first part of this chapter. This is a practice problem 4.1. Here we have 5 questions regarding to the heat engine. So please complete the entire question given in this slide. This is another part of the practice problem 4.1, and it is include the heat engine and the refrigeration system. This is another part of practice problem 4.1, and this question will include the problem of refrigerator as well as the heat pump. Okay, on this slide, so the practice problem 4.1 is include the heat pump and the Carnot cycle. Okay, this is the last part of the practice problem 4.1. The question on this slide is combining all the knowledge on these topics. So, please complete the entire question to test your understanding on this topic. With that, thank you very much, and please stay safe wherever you are. So see you on the next video. Wassalam.